The aim of this superstructure assignment is to develop an understanding of structural design process to help us work efficiently with engineers and other consultants when you're engaged in work in the field. A key aspect of working with structures in the construction industry is being able to think critically about potential risks and issues, design solutions to respond safely and within the parameters of Australian codes and regulations, and then be able to communicate your ideas with confidence, which is the aim of this assessment. We firstly did some research about members involved in a commercial building and how they work in transferring and carrying the loads. To help with this, we not only did online research, but also went on a site visit to the University of South Australia's Mawson Lakes campus, where we got to analyse construction members as well as concrete mixture testing. Columns are vertical structural members that transfer the vertical loads to the foundation through the footings by compression, most commonly used in the outer frame or shell of the structure, but can be used inside the structure depending on the size and type. Beams are horizontal structural members between columns. They are used to support loads and transfer them across their length to the columns, which are then transferred into the building's footings and then the foundation. They are also used to carry the moment or rotational force of the structure. A rafter is a type of internal beam that holds up the building's roof loads or weight from above and constitutes a roof framework. It is connected between the columns and beams at one end and the ridge or apex at the other. The ridge is also another horizontal member like a beam at the top of the structure. Purlins are used as a smaller horizontal beam member that sit on top and are supported by the rafters. Purlins are specifically used to carry the roof deck sheeting loads specifically. Girts are also horizontal structural members inside a structure, but used specifically on the wall, not the roof. They are quite similar to purlins as they provide lateral support and hold the wall cladding to resist wind loads. A purlin can experience flexural torsional buckling of the compression flange when it is not restrained. To stop this, bridging can be used. Bridging is a tension member used to limit the deflection of a purlin in the direction of the weak axis. It is connected between spans of purlins that are perpendicular to the rafters. Girts also have bridging, but it is not needed as much. Bracing is used through specific sections and areas of industrial buildings depending on the location, shape and uses of the building. They can be spanned diagonally between rafters and columns. Depending on the direction and location of the span, bracing can support the building in either tension or compression. Connections also play a big part to how the members react. Rigid or fixed connections are used in industrial buildings to resist or support vertical, horizontal, and rotational movements of the structure. This means that a structure needs at least one rigid connection to cover the moment of the structure. Pinned connections are the second most commonly used and strong connections seen on industrial buildings. They help resist the vertical and horizontal movements of a building. These can be used in all locations of an industrial building and depending on its use can look or be constructed differently. On top of the members, the loads applied are also a great factor. On a commercial or industrial building, live loads, dead loads and wind loads are most commonly present. Live loads change over time or are not permanently there. Dead loads are always present within the structure, mainly through the self-weight of members. And wind loads are affecting the structure in both pressure and suction or positive and negative forces. For our group specifically, in designing our domestic shed, on top of the generic dimensions given, we had a span of 4 metres and height of 5.2 metres, within being in wind region A and a wind terrain category of 3. We had to determine and design the loads applied on the building, purlins, girts, bracing, columns and rafters, using lysite products for the roof sheeting, purlins and girts, and 1 steel universal beams for the columns and rafters. The connections are also to be pinned or a braced box structure. Our calculations were done in accordance of multiple Australian standards as well as multiple different capacity tables. Firstly, we determined the wind load on the building consisting of the wind speed and net pressure or the suction and pressure acted on it. We found that the serviceability state was at 32 and the ultimate bearing capacity was at 50. For purlin design and selection, it took multiple times to find the most economic and safe section, but found that the Lysite Z219 met the design parameters. The Gert, much like the purlin, it took multiple attempts to find the correct section, but we found that the ZC219 section was sufficient for the serviceability. No live load was considered in designing the Gert. For the wall sheeting material in particular, section of ZC224 was sufficient. After designing the purlins and Gerts, we then were able to design the rafters and bracing of the structure, which helped carry the self-weight of the purlins and roof sheeting, along with help send the loads to the footings through compression and tension. For roof bracing design, the ultimate pressure was found to be 0.55 kPa and suction to be minus 0.47 kPa. The forces that the end and intermediate frames will experience are then calculated. Diagonal members in the roof bracing are only resisting tension. Therefore, we can remove the members that will be acting under compression. Due to the symmetrical shape of the bracing, both BY and FY equaled 15.92 kilonewtons. This information is then entered into a computer program, SpaceGas. SpaceGas then calculates the force in each individual member. As both sides are exactly symmetrical, only half of the members' forces need to be determined. Members that are negative are acting under compression, and members that are positive are acting under tension. For members under tension, equal angle sections can be used, and for members under compression, rectangular hollow sections can be used. These sections are the best to use as they are the most economical while still being able to carry out the amount of load it will experience. Wall bracing is quite similar to roof bracing in the calculations. It was found that the force in the tensile diagonal member is 41.39 kilonewtons. A suitable equal angle section must now be selected from the capacity table. The smallest section can for this wall bracing, which is 50 by 50 by 3 EA. As well as being able to sufficiently carry the load, it will also be the cheapest possible section. For rafter design, the rafter self-weight is assumed, as we don't know what section will be suitable for our structure. After the try and error, we can have a more realistic figure. We found that the end rafters could use 150 universal beam 18 with fly bracing. The central rafter had to be able to carry a car load of 500 kilograms, but through the calculations, we found that we could still use the same section as the end rafters. Finally, we designed the vertical column members that support the actual compressive load being transferred from the roof to the footing. As they are pinned connection, lateral load does not need to be considered. The column design was able to be found first try with a section of 100 universal column 14.8. It is noted that this design is not very economical due to the additional capacity, but it is still the smallest column and still safe for the central column. Seen above is a sketch of our structure's lateral and gravitational load paths. The sketch is taken from the middle column is to illustrate the extra point load it is experiencing. Therefore, there are no Gerts present as there is no wall. The lateral load sources come from the wind, and the gravitational load sources come for the point load as well as the uniformly distributed load. The loads are transferred from the rafters to the columns, which in turn transfer the load to the slab and the footing pads, which transfer the load into the foundation. Throughout this assignment, we learned many things about the design processes of different structural members. As a group, we were able to design purlins, bracing, rafters, and columns for a warehouse with the parameters as mentioned on the cover sheet. The knowledge gained from this assignment has been invaluable and will definitely aid us when we enter the industry as construction managers.